Hello, lazy chemists, and welcome to today's lecture, which is going to be on the concept of intermolecular forces. Okay, and for some of you, this is going to be a little bit of a review, and for others of you, this is going to be a fresh, brand new topic. But it's really something that's really fairly simple to understand, because what's going on here is that we have forces that are happening in between molecules. So one of the things that we like to go ahead and talk about a little bit with molecules is what their boiling points are and things like that, and whether they're a solid at a particular temperature, or if they're a gas at a particular temperature, and all of the factors that affect that have to do specifically with the intermolecular forces, or the forces that are in between the molecules. Okay? And there are a couple of forces that are in play, and we're going to go ahead and do a brief overview of them first, and then we're going to go into a little bit more detail on them in just a second. So we're opening this one up, and this one's our more basic idea. Okay? And the first force we're going to go over is one of the stronger ones, and it's going to be a dipole-dipole force. Okay? And this is when we have polar molecules. And what happens with the polar molecules is that the negative side or the positive side of that molecule, whichever side has a negative end and which side has a positive end, those are going to interact with each other. Okay? And they're going to interact kind of similar to magnets. Okay? And when they interact with magnets, it means that they're going to hold on fairly strongly. Alright? So dipole-dipole is kind of a strong force that's holding things together. And this happens between all polar molecules. Okay? And and even when it's a liquid, what's happening is that you're having those intermolecular bonds, those dipole-dipole bonds, are going to be created by this partial positive or this partial negative charge. And they're going to temporarily be attracted to each other. And that's what holds liquids together. And this is one of the things that holds something like water together. So when water is a liquid at room temperature, you have to think like, oh, why is it a liquid at room temperature? And it's because it has these partial negative and partial positive charges. Whereas other compounds, even if they're heavier for water, if they don't have the partial negative and partial positive charges, they're not going to be able to hold together quite as well. Okay? The next type of force is a London force. Okay? And this is also called the London dispersion forces. And London dispersion forces are forces that are more keenly attributed to like the size or the mass of a compound. And what happens in a London dispersion force is that those electrons that are in a compound are randomly moving all over the place. And when they randomly move all over the place, you're going to sometimes get some moments where you're going to have some unequal amount on one side, and you'll get a temporary charge. Or you might get an induced charge when a charged particle enters that system and creates a temporary charge. And what happens with these is the larger the molecule, the greater the chance that there's going to be some London dispersion force happening, and therefore we usually say that London dispersion forces scale up specifically with size. Okay? And this is another example here. Oh, that's a terrible. So here it's showing like a dipole interaction and London dispersion forces. But in general, London dispersion force, I usually end up liking to call it the fat force. And the reason that I call it the fat force is that the larger the molecule, the larger the London dispersion forces are going to be for that molecule. Okay. And the next one is hydrogen bonding. Now, hydrogen bonding is an example of a dipole-dipole bond. Okay. And what's special about hydrogen bonding in particular is that let's go ahead and pull this up. Let's join. Man, this would have been good to have prepared beforehand. What's special about the hydrogen bonding in particular is that it's essentially just a dipole-dipole bond. But normally with a dipole-dipole bond, so let's go ahead and say that we have like Cl here, and let's say that we have like, what's something else that could be on the side here? What would have like a positive charge? Like, you know, Okay, let's do S here. Okay. So, a typical dipole-dipole, what would happen is that you would have this bond here, but this bond would, or this sulfur especially, would have some outside electrons that kind of shield this bond from being as strong as possible. Okay? But if you have a case where you have a hydrogen bond, that hydrogen doesn't necessarily have that kind of a shield. And the reason that it doesn't is because hydrogen only has one electron. Okay? So, the hydrogen bond, so we'll go ahead and put dipole here. The dipole bond kind of has a shield in between from making it as strong as possible, whereas the hydrogen bond has no shield. And the reason for that is just because, you know, hydrogen's electron is in here, okay? It doesn't have an electron cloud in between. Therefore, it's going to form a stronger bond, okay? And that stronger bond that happens because of hydrogen bonding is really why water ends up being quite as strong as it is. In fact, water is one of the strongest in terms of intermolecular forces for its size for covalently bonded molecules. Okay, and this also ends up affecting not just boiling points and melting points and all that, but it's also going to affect the viscosity, okay, or the resistance to flow. That's what viscosity is. So whenever you hear viscosity, you're going to be talking about how resistant something is to flow. Okay. All molecules will take part with London dispersion because all will have mass. Not all will take place in dipole-dipole. Those will only be the polar. And then, again, if it has hydrogen bonding, so if it has unequal bonding with hydrogen, it's also going to be an important factor for its viscosity there. Okay. Now this one goes a little bit more in depth, and so we're going to go ahead and start this one right here. Okay. And this one essentially is having us kind of think through some of the processes here. Okay. Now we've already gone through these right here: London dispersion, dipole-dipole. Network forces, we'll get into that when we get into the solids. And we also need to know that they're weaker than the intramolecular forces. So things like a covalent bond and an ionic bond are going to be a lot stronger than any of the intermolecular forces. Okay. So, here we have an example where we have sodium chloride. Okay. Sodium chloride melts at 801 degrees Celsius, yet butane melts at 159.6. Okay. Now, both of these molecules, both sodium chloride and butane, have similar molar masses, so they weigh the same. Okay, it's the intermolecular forces that affect this. Okay, and we can say pretty safely that sodium chloride has stronger intermolecular forces than butane because it melts at a much higher temperature. Okay, sodium chloride is an ionic solid, which means that all of these charges, we have full charges that are holding these together. Okay? What I'd like to also do to help explain this is use the law that we were using before, which is Coulomb's law. Okay? And in Coulomb's law, what's happening here is that we have Q1 and Q2. Okay? Now, most of the time, when we've been talking about things, we've been messing with R. We've been messing with bond length and with R. However, when we're working with ionic solids, what we're doing is we're increasing Q. And Q, when Q is a whole number, it's going to be really tightly bound. Okay? And that's what's happening here. We have a really tightly bound compound because it's a full-on number. Okay? We have sodium, which is a full number, with chlorine, which is a full number, and that's a super strong connection there. That's a super strong bond that has happened there. Okay? Butane, on the other hand, and this is what butane looks like, butane doesn't have any of that. Notice that we don't have any of, firm base charges. Okay? We don't have any kind of polarity. In fact, we have no charges on this molecule. Okay? Which means that this molecule doesn't have those ionic charges holding it together, and it doesn't have any dipole charges holding it together. So essentially, Q1 and Q2 ends up being really small, so there's no charges going on this. Which means that the only thing that is affecting how this boils is how large it is. Okay? Which means that a lot of organic compounds like this that are really, really large, that are going to be dependent, their boiling point is going to be dependent upon how large they are, and that's the only real factor that affects them. Okay? And yeah, this is exactly what this one says. Alright, so let's go ahead and take a look here at another example. Okay? This right here is an example of a boiling point trend. Here we have H2O, we have hydrogen fluoride, we have NH3, and we have H2S2. Okay? Notice that H2O is the strongest bond. Okay? Okay? And in order for us to have hydrogen bonding, we need it to be bonded either to an oxygen, fluorine, or nitrogen. Okay? And the reason for that has to do with the electronegativity. And oxygen, fluorine, and nitrogen are the three that are most keenly going to be able to take that electron from hydrogen. And when they take that electron from hydrogen and make it so that the electron has to stay here, that's when we're going to get the hydrogen bonding. Alright? Whereas in this previous one, this one right here, carbon doesn't have enough electronegativity to take that electron. Okay? So that means that you'll only see hydrogen bonding when you have it with oxygen, fluorine, and nitrogen. Okay? And this is a point that if you need to go ahead and copy down this specific bit of information here, I will allow you to, I would suggest you pause it and then copy it down if you need so. But realistically, the three things that you need are oxygen, fluorine, and nitrogen make hydrogen bonds. Okay? Alright. Next, we're going to go ahead and talk about when we take ionic bonds, we end up separating them out into the water. And what will happen is that we will go ahead and do what's called an ion-dipole interaction. Okay? And an ion-dipole interaction is essentially the interaction that happens when we have an ion bonding or connecting with a dipole. Okay? So here what's going on is that the chlorine is going to go ahead and bond in with the hydrogen side right here. And this arrow is terrible because it's trying to point here. But the chlorine is going to bond to this hydrogen side of the oxygen, of the water molecule. And then the negative side is going to bond with the sodium. And so when sodium chloride dissolves in water, we call the bonds between sodium chloride an ion-dipole interaction. And those are really, really strong as well. If you think like, hey, we have a positive charge connecting with a partial negative, those are going to be fairly big because we've messed with Q now. Q is fairly large for at least one of the particles involved. And that's what's going on when we dissolve a salt in there. We have an ion-dipole interaction. Okay? And this right here is explaining our London dispersion forces. And it's using fluorine, bromine, and iodine. Fluorine is F2, bromine is Br2, and iodine is I2. And fluorine is a gas at room temperature. Chlorine is also a gas at room temperature. Bromine is a liquid at room temperature because it's larger than the other two. And then iodine ends up being a solid at room temperature. And it doesn't take very much. You can actually melt iodine, well, not melt it, but sublime iodine really quickly to get there. Okay? Alright, and an example, fluorine has the smallest molecular size. And it's really molecular size. That's the biggest thing here. And atomic mass isn't so much the biggest thing here for why it's evaporating. It really is more to do with the size of the molecules. And then this one here is explaining how bromine is just a little bit stronger, because it has a lot more space. It has a lot more space, to create those localized charges. And then iodine is the largest. Okay. And this is another example where we're trying to say, like, oh, the gravity of an asteroid, so fluorine is an asteroid, and it doesn't have enough mass to, pull in all the other ones. Though, like, eventually, like, theoretically it could. Like, just, everything's affected. I don't know that I like that analogy. Alright, and this one's iodine. Iodine is the moon moving. Okay, this one, number 5, is trying to explain the sublimation of carbon dioxide and iodine. So both of these things don't really exist for, in a in-between liquid state. Iodine is composed of covalent bonds, and so is, carbon dioxide. And the only real forces that are holding them together are the van der Waals or the London dispersion forces. Okay, so two iodine things are only being held together by London dispersion, and then when you break those, like, they're completely broken. Okay, so as soon as you give iodine or carbon dioxide enough energy to break apart from each other, to escape so that they slide past each other, once they are able to slide past each other, they're able to just escape from the entire structure in general. Because if they have enough movement, if they're no longer tightly packed together, they're just able to run away and escape. And that's essentially what's going on with carbon dioxide and iodine, that as soon as they get enough movement going, they're gone. Like, it's just absolutely gone, is the best way to describe it. Because the only force that's holding them together is the London dispersion forces that we went over before. And also, real quick, if you ever draw carbon dioxide like this, like automatic failure, it needs to be a linear molecule every time. Man, I didn't notice this before. Man, oh my god. It needs to be a linear molecule. If it's not, then it's going to have intermolecular forces at play, but since it's a linear molecule, it doesn't. Okay. And this is talking about diamond and quartz. Both of those are known as network solids, and we'll get into them in a little bit more detail. But basically, they make these huge networks of covalent bonds in between each other. Okay? And when that happens, all of those network covalent bonds take a lot of energy to break apart. Okay? Because those network covalent bonds are no longer in between molecules, but they're within the molecules. Okay? So it's kind of like it makes a much stronger bond that keeps going and building off of each other. And then I'm going to go ahead and end us there for today. I mean, I think that there's a couple more dissolving these things in work. Okay. I'm going to go ahead and end us there for today. It's a fairly long lecture, but it should cover a good amount. Our next one is just specifically on hydrogen bonding. And we're going to go ahead and delve into that and also delve a little bit closer into hydrogen bonding, especially in regards to proteins and protein structures, because I think that'll probably be the most useful thing for everybody. For now, I want you to go ahead and just ruminate on intermolecular forces, and then remember that if you have the chance, remember to be lazy.